Good morning. My name is Don Lamb, and this summer at the NASA Goddard Space and Flight Center in Greenbelt, under the mentorship of Dr. Robert Benson and Dr. Yangli Wang, I observed the effects of summer and winter geomagnetic storms on the electron density of the F layer and the topside ionosphere of the atmosphere. Now, I'm going to provide some background information about my project. A geomagnetic storm is a highly condensed collection of charged particles that have escaped from the gravitational pull of the sun due to traveling at extremely high speeds. These storms often travel in random directions out into space. However, when they travel towards the Earth, these storms collide with the layer of the atmosphere known as the ionosphere. As they travel through the ionosphere, because the ionosphere is made up of ions, the storms constantly lose electrons. If you are familiar with the northern lights and other auroral phenomena, you are actually observing a geomagnetic storm as it travels through the ionosphere. The electron density is a measure of the number of electrons per cubic centimeter of space. Because these storms can collide from any direction, the electron density of the ionosphere is not uniform throughout the year and is an interesting phenomenon to observe. Previous studies have conclusive results in the high latitude and mid latitude regions of the Earth. However, my study focuses on the low latitude regions of the Earth, which lies in between negative 20 and 20 degrees latitude. The first step was to define summer and winter in a quantitative manner. I used the Julian calendar, a calendar that represents each day of the year as a number from 1 to 365, beginning from January 1st. I defined summer from the beginning of June to the end of August, or 152 to 243 on the Julian calendar. Likewise, I defined winter from the beginning of November to the end of January, or 305 to 031 on the Julian calendar. The next step was to determine which satellites I was going to use in the study in order to collect my data. I chose the Alouette and the ISIS-1 satellite, not only because the data was convenient to access, but there are also two of the four most successful satellites to be launched into the ionosphere to collect data about the electron density of the ionosphere. The next step was to find the dates during which geomagnetic storms occurred. I used a parameter called DST in order to track these storms. DST is measured in nanoteslas and measures the strength of a magnetic storm. The more negative the value, the stronger the storm. The typical geomagnetic storm can record a DST value of at least negative 50, but stronger storms can record values up to negative 200, which are often called superstorms at that point. I began my search in 1973 because that was the year during which the Alouette and the ISIS were first launched into orbit. The next step was to find the ionograms which are digital representations of the fluctuations of electron density caused by the storms for these dates. I used the ISIS and Alouette homepage provided by my mentor in order to find and download these ionograms. Next, I used a tool called the Space Science and Visualization Program, a tool provided by my mentor, and SSAV for short, to make corrections to the ionograms, if necessary. The data from the satellites I used in this study were originally not adapted for digital conversion, so sometimes the data would have incorrect time markers or whole sections of the ionograms would be missing and be attached to the next ionogram listed. The last step was to use the SSAV to generate an electron density distribution, a pictorial representation of the electron density compared to altitude, which was measured in kilometers, and graphed them in Excel. Now, I want to give some information about my results before I show them. The following four graphs represent the electron density distributions for the data I collected. I collected data during four different time periods: summer during the daytime, summer during the nighttime, winter during the daytime, and winter during the nighttime. Each graph has one line showing the electron density the day before the storm, and one line showing the electron density during the action period of the storm. Once the geomagnetic storm has penetrated through the ionosphere, all the storms were recorded at -3 to 2 degrees magnetic latitude in order to assure that the latitude was not a contributing factor in the analysis. The first storm I recorded occurred on between July 5th and 6th in the year 1974. the the profiles were recorded in Ouagadougou in Burkina Faso. The lowest DSC value in this graph is -204, which occurred at 7 a.m. This storm was the strongest magnetic storm in this study, and it is interesting to note that the electron density of the action period of the storm is less than the electron density during the storm. The storm that I observed during the nighttime in the summer occurred in July of 1978 between the dates July 4th and July 5th. The lowest DSC value in this graph is -99 nanoteslas, which occurred at 7 a.m. An observation of note is that the electron density during this storm was higher rather than lower than those before the storm, which shows an opposite behavior from the summer daytime graph despite being taken at the same magnetic latitude. The next graph was recorded during the daytime during the winter time. The lowest DSC value was -93 nanoteslas, which occurred at 2 p.m. This graph shows the same pattern as the summer daytime storm, where the action period of the storm actually shows a electron density that is less than that of before the storm. So we can be confident that the first graph is not due to some random chance, and that even a different season shows the same pattern. Now, in the final graph is a winter storm during the nighttime, which occurred in November of 1974, in between November 7th and November 8th. This graph exhibits a similar behavior as the summer nighttime graph, so we can also be assured that for this graph, the nighttime pattern is not due to some random chance. Now, in order to determine whether or not the difference in electron density for these graphs was significant or not, I use a statistical analysis, or a t-test. Table 1 shows the analysis of the electron density in the F layer before and during the summer winter daytimes and the nighttime geomagnetic storms. Table 2 represents the same kind of data, but in the topside ionosphere, which is from 400 kilometers to 1,000 kilometers. Table 3 shows the analysis of the electron density in the F layer when comparing the day before the storm versus the day during the storm. And Table 4 shows the same data taken at the topside ionosphere. So, what I could conclude from my data was that in the F layer, under normal conditions, or the day before the storm, the daytime electron density is greater than those during the night, and that during the action period, it was observed that the electron density of the nighttime storms were greater than those of the daytime storms. The topside ionosphere showed similar cases to those observed in the F layer. However, there are some cases in which the difference in electron density was not statistically significant. The most probable I did further research into what could have caused this phenomena, and the most probable cause was the switch from the dominant ion from oxygen to hydrogen when transitioning from the F layer to the ionosphere. The atomic mass of oxygen is 16, while the atomic mass of hydrogen is only 1. So, oxygen is capable of bonding to 16 other ions, while hydrogen is only capable of binding to 1. So recombination is much more unlikely when hydrogen is the dominant ion, and thus the electron density would not change very much as the storm traveled through the ionosphere. So you may be asking yourself, why does this all matter? If we can better understand geomagnetic storms and how the electron density of the ionosphere changes, it may be possible to harness the energy of the ionosphere. Because there are so many massive bodies in space, it is reasonable to conclude that the ionosphere has generated much more usable energy than has ever been generated on Earth by mankind. There is a NASA project in development called the Electrodynamic Tether, a cable that uses the kinetic energy of ions to power various machinery such as satellites. The electrodynamic tether would extend outward from a satellite, and as it orbits around the Earth, ions in the ionosphere will collide into the tether, and their kinetic energy will be converted into usable energy for the satellite. The electrodynamic tether is so powerful that some developers believe that it has the capability to save the US millions of dollars by eliminating the necessity of propellant for the International Space Station, which normally costs about $7,000 per pound, by setting up a series of electrodynamic tethers around the exterior of the space station. The ability to harness this energy could also lead to groundbreaking advances in medicinal technology, such as the possibility of precision tumor destruction and medicinal healing. There have been studies in which plasma has been inserted into a damaged tissue, and they observed that the plasma stimulates regeneration without disrupting the other processes of the surrounding tissues. I'd like to acknowledge my mentors, Dr. Robert Benson and Dr. Yangli Wang, for sparking my interest in heliophysics and providing me help when I need to understand something for my project. I'd like to thank all my teachers at Poolsville High School, especially my biology, chemistry, and physics teachers, whose studies helped me understand many of the inner workings of different aspects of space for my project. I would like to acknowledge Ms. Diane Cockrell, the leader of the National Space Club Scholars and the head of the internship office at Goddard, for giving me the opportunity to conduct research there. And lastly, I would like to thank my parents and other kids' parents for driving me to and from Goddard every day. These are some of my references, and I would like to open the floor to questions. Thank you.